In this video, we're going to talk about the inner product. So our goal is to use this notion of the inner product to impose geometry on Rn. So we can talk about things like length and distance and angles between vectors and orthogonality, which we talked about in the overview video. This is just another word for perpendicular. Or I guess technically orthogonality would be a noun. So perpendicular, maybe I'll say perpendicularness. Okay, and projections. Okay, so let's begin with a definition. So let's define what the inner product is. So if u and v are vectors in Rn, we'll define the inner product, and the inner product is sometimes also called the dot product. So the inner product of u and v is going to be defined as, so first, here's my notation for the inner product. I write the vectors u and v with a dot in between them. So because u and v are in Rn, I've written them with n entries. So u1 up to un for the vector u, for example. So here's the definition. If I want to take this inner product, what we do is we transpose u, and you multiply that transpose times v. Okay, so the transpose of u takes this column vector and turns it into a long row. It'll turn it into u1, actually let's put this in green. It'll turn it into u1 dot 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 up until un, and then I'm multiplying by v now, so v1 is still a column vector, v1 dot 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 up until vn. And then when we do this multiplication, we multiply this row times this column. So that gives us u1 v1 plus dot 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 up until un vn. Okay, so there are a couple of things that I want to observe about this. So the first is, one way I could think about this output is, what we're sort of doing is we're multiplying the two vectors entry by entry, and then we're taking the sum. So these two vectors right here, we're sort of multiplying them entry by entry. So u1 multiplies the v1, u2 multiplies the v2, and so on, and then we sum all of those. The other important thing about this is, when we take an inner product of two vectors, notice that the input are vectors. So we're inputting two vectors, u and v, and we're performing some operation on them. But then the output, this number right here, u1 times v1 and so on, is scalar. Because this just involves the entries, and the entries being multiplied together and then summed. Okay, so next let's define some other terms. So let's define next what the length of a vector is. So if u is a vector in Rn, we say that the length of u, so that's sometimes also called the norm of u. So this is defined as, so the notation for length is we write these double sort of absolute value looking bars around our vector. And that stands for the length. So the length is defined to be the square root of u inner product with itself. Okay, so if you inner product u with itself, you'd end up multiplying, the entries of u with themselves term by term. And that'll give us, instead of u1 times v1, we'd have u1 squared plus dot dot dot. And instead of un times vn, we'd have un squared. And we're square rooting that whole thing. So the length of u is this thing. It's the sum of the squares of the entries being square rooted. But notice that this square root term, it looks like the Pythagorean theorem. And that's good, because we want this inner product to be imposing geometry on Rn. So it's good that a term like length, the formula for it looks like what we'd expect from geometry in just R2 or in R3. Okay, so now let's define what the distance between two vectors is. So if u and v are vectors in Rn, the distance between u and v is defined to be the length of u minus v. And it doesn't matter the order that I subtract them in. So if I did v minus u, that would be the same thing. Okay, so let me look at a picture to explain where this is coming from to motivate this. So let's draw a picture in R2. So in R2, I'm going to draw some axes, and then I'm going to draw some vectors. So let's say that my vector v looks like this, and then the vector u, let's say, looks like this. And then there's some angle between these two vectors. So I'll call that theta. And now let's draw one more vector. So now I'm going to draw the vector starting at the tip of v, connected to the tip of u like this. So that vector right there, this is u minus v. Because when I line up, if I sort of add v to u minus v, I would expect to get this vector right here. I would expect to get this vector if I sort of line them up and use the parallelogram rule. But notice that if I add v to u minus v, the v's cancel and I get u. So this orange, dark orange, I guess, vector is u minus v. Okay, so now let's write down the lengths of these vectors. So if we write down the length of u, and let's just square it to get rid of the square root. So if we were to think of u in terms of its entries as being u1 and then u2, and there's just two entries because we're thinking of these as vectors in R2. So if you were to square that, the length of that vector is u1 squared plus u2 squared. And I don't have the square root in here because I've already squared this. And that's just coming from the Pythagorean theorem. So if we did the same thing with the length of v, and we squared that, we'd get v1 squared plus v2 squared. Now let's also write the length of u minus v. And let's square that. So for u minus v, I'd be using the distance formula to get this distance. So I would be sort of subtracting the entries of u and v and doing the distance formula. And that would give me u1 minus v1 squared plus u2 minus v2 squared. And again, this is just coming from the distance formula. But now let's expand this out. So if we expand this out, the right-hand side becomes, we get u1 squared minus 2u1 v1 plus v1 squared. And then from the second square term, we get plus u2 squared minus 2u2 v2, and then one more term, plus v2 squared. Okay, so the next thing that I want to do with this triangle that I formed here is I'm going to use some pre-calc. Some more heavy-duty machinery in pre-calc. I'm going to use the law of cosines. So the law of cosines. Okay, so if I do the law of cosines on this triangle, it tells me that the length of the side that's opposite theta to the length of u minus v squared is equal to the length of u squared plus the length of v squared minus 2 times the length of u times the length of v times the cosine of the angle in between them. So if you don't remember the law of cosines, that's totally fine. I'm talking about it here to sort of motivate a key geometric result about the inner product. So don't stress too much if you don't remember this or if you haven't seen it before. Okay, so what I'm going to do now is, for the left-hand side, the length of u minus v squared, I'm going to replace it with this expansion that we did. Okay, and I'm going to replace these two squared terms on the right-hand side, so the length of u squared and the length of v squared, with their respective expansions that we did here. And in doing that, there are a bunch of terms that are going to cancel out. The terms that will cancel out are all of the squared terms, basically. So the u1 squared would cancel out with this u1 squared, This u2 squared would cancel out with this u2 squared. The v1 squared would cancel out with that v1 squared. And this v2 squared would cancel out with that v2 squared, because they're on opposite sides of this equation. So what that will leave us with is negative 2u1 v1 minus 2u2 v2 on the left. And on the right, we'll have negative 2 times the length of u times the length of v times cosine of theta. All right. And now I can divide both sides by negative 2, and that'll give me u1 v1 plus u2 v2 equals the length of u times the length of v times cosine of theta. Okay, so now there's something that I want to notice about this. So what I want to notice is if we think of v as the vector v1, v2, which we've sort of implicitly been doing here, because I wrote it in terms of the entries over here. Notice that this left-hand side is actually the dot product of u and v, because we've multiplied the entries of u and v, term entry by entry, and then we've summed them. So we've just shown a key result about the dot product. So I'm going to state this as a theorem. So in R2, and it turns out also in R3, the argument that we just gave here holds. The dot product of two vectors, u and v, will be equal to the length of u times the length of v times the cosine of the angle in between them. So what this demonstrates is sort of a geometric interpretation of what the dot product is in terms of the angle between two vectors. So kind of as an aside, in higher dimensions, so higher than R3, this formula is actually what's used to define what an angle is, because we can't really visualize angles in dimensions higher than R3, so we use this formula to define what an angle is. Okay, so let's next give another definition. So next I want to define what it means for two vectors to be orthogonal. So we say that u and v are orthogonal, and that's another word for just perpendicular, if their dot product equals 0. And in that case, a common notation that we'll use is we'll write u. This is a perpendicular symbol, the sort of upside down t, and then we write v. So let me give a visual picture for this. So in R2, so I've gone ahead and drawn in some xy axes. So let's draw a couple of vectors that look orthogonal, that look perpendicular. So let me draw a vector v, and let's draw a perpendicular vector u. Maybe u is a little bit longer. Okay, and then let's say that these two are perpendicular. So in this case, if these two vectors are perpendicular, then their dot product, according to this definition, u dotted with v, better be equal to 0. So u and v are orthogonal since the angle, just sort of geometrically, since the angle between them is 90 degrees, or in radians is pi over 2. And why this sort of matches up with the theorem that we had shown up here is if the angle between the two vectors is pi over 2, let's think about what this cosine will be. So what's the cosine of pi over 2? Well, cosine of pi over 2, cosine of 90 degrees, that is 0. So because the cosine of pi over 2 is 0, this cosine term becomes 0, and that means that the dot product of u and v is going to be equal to 0. So that's why when we have vectors that are perpendicular to each other, their dot product should be 0. Okay, so now let's do an example. So let's let u, v, and w be the following three vectors. So let's practice computing some dot products first. Let's compute u and v, u dotted with v, and then u dotted with w. Okay, so first let's do u dotted with v. So I'm really going to practice using my notation for u dotted with v and that transpose notation. So this is u, transpose times v, and u transpose is 1, 2, 3. So this column has turned into a row, and then times the vector v. So 2, negative 3, 4. And now multiplying these, I would get 1 multiplied with 2 plus 2 multiplied with negative 3 plus 3 multiplied with 4. And if we work this out, we'll get 2 minus 6, so that's negative 4, added to 12, which is 8. So we end up getting 8. And the fact that this dot product is not 0, so this is not 0, means that these two vectors, u and v, are not orthogonal. So that's pretty nice that this dot product tells us something tangible, something geometric about these vectors, whether they're perpendicular or not. Okay, so now let's do the dot product of the other two vectors. So let's do u dotted with w. So that'll give me u transpose times w. So u transpose again is the same as before, 1, 2, 3, written as a row. W is negative 4, negative 1, 2. And multiplying these, so we'll get 1 times negative 4 plus 2 times negative 1 plus 3 times 2. And adding these up, we'll get negative 4 minus 2, which is negative 6, added to 6, which is 0. So the fact that this dot product equals 0 means that u and w are orthogonal. So they're going to be perpendicular. So next, let's find the length of u. So let's find the length of the vector u. So let's recall that the formula for this, so the formula for the length of u was we took the inner product of u with itself, and then we square root that. So sometimes I'll be using the terms inner product and dot product interchangeably. So for our purposes right now, they both refer to the same thing. But I'll do my best to try to use the term inner product as much as possible. Okay, so when we dot u with itself, what we'll get is we'll get 1 squared plus 2 squared plus 3 squared. And then we got to square root that. So we get 1 plus 4 plus 9, which is 14. So square root of 14. And that's how long the vector u is. We've determined its length. Okay, so let's do another part to this example. Next, let's find the distance between the vectors u and v. So to find the distance between them, we take the length of u minus v. And it doesn't matter the order that we subtract them in. Okay, so u, let's remind ourselves, u was the vector 1, 2, 3. So we're subtracting the vector v, which was the vector 2, negative 3, 4. So we're subtracting these two vectors, and then we're taking the length of that result. Okay, so if we subtract these two vectors, we'll get negative 1, 5, negative 1. And then we want to take the length of that. So the length of this vector. So using our formula for the length, we'll get negative 1 squared plus 5 squared plus negative 1 squared. And then we square root that. So this will be 1 plus 25 plus 1, which is 27, square rooted. And that's the distance between u and v. Okay, so next I want to define another term related to lengths. And that's this idea of a unit vector. So recall that in the example that we just did, the vector u was 1, 2, 3, and its length was square root of 14. So that was something that we computed. So to get what's called a unit vector, and the word unit just means that we want it to have a length of 1. So to get a unit vector in the direction of the vector u, what we do is we multiply u by the scalar 1 over the length of u. Okay, so what that implies is if you take the vector u and you divide it by its length, this resulting vector will have length 1. So this works as long as the vector u is not 0. because if it was the 0 vector, then the length of it is going to be 0, and we're not allowed to divide by 0. So let's check this. Let's check this for the vector u that we have. Okay, so let's take u, and let's divide it by its length. Okay, so when we divide it by its length, that means we're multiplying by 1 over the length. So 1 over, and the length we already found was square root of 14. So we're multiplying that by the vector u, which is 1, 2, 3. So we multiply this fraction into all of the entries. So we'll get 1 over root 14, 2 over root 14, 3 over root 14. So this right here is a unit vector. This should be a unit vector. A vector of length 1 in the same direction as the vector u. So this process of making a unit vector, so this is called normalizing. This is called normalizing a vector. So if you guys have taken multivariable calculus before, some of the terms that we've talked about in this section should be familiar. So things like normalizing a vector are things that we typically do in multivariable calculus as well. Okay, so now let's just check that the vector that we got actually has a length of 1. So let's compute the length. So the length of this would be, so I square all the entries, so 1 over root 14 squared, and then I sum them, plus 2 over root 14 squared, plus 3 over root 14 squared. Sum them, and then we square root that. So squaring these, I'll end up with 1 plus 4 plus 9 over 14 square rooted, and simplifying this, I get square root of 14 over 14, which is 1. So that's good. So the length of this unit vector is in fact 1. Okay, so that checks out. Okay, so what I want to end this video by doing is listing some properties of the inner product. Alright, so if u and v are vectors in Rn, and c is a scalar, then the following properties hold. So for example, property 1 says the inner product commutes. So the order in which we take the inner product doesn't matter. Property 2 is distribution. So if we take the sum of two vectors and then dot that, take the inner product of that with a vector w, that w distributes to each of these. Property 3 says if we have a scalar sort of floating around in this inner product, so if the scalar is multiplying u, I'm allowed to move that scalar either in front of the whole inner product or move that scalar and have it multiply v. And the fourth property here says that when you take the inner product of a vector u with itself, that is always going to be greater than or equal to 0. And moreover, the only way for that inner product to be equal to 0 is, so that happens if and only if the vector u is the 0 vector. Okay, so for this fourth property, just really quick to see why this is the case. So remember that u inner product with u is the length of u squared. So the length of u, so anything squared should be greater than or equal to 0. And the final thing that I want to note is, if we take the length of a vector u times a scalar, I can pull this scalar outside of this length operator, but when I do that, I need to put an absolute value around it. And that's important because if I'm multiplying by like a negative value, so if c was negative, well, the length operator is supposed to give me a non-negative output. So having these absolute value bars around z are important to ensure that.